Well, one application of orthogonal matrices has to do with conic sections, as I was talking a little bit about yesterday. And namely, if you've worked with conic sections, I'm not sure if they do this. I'm not sure if they're required to teach it nowadays, but I can recall when I was working with conic sections in Calc 2. I didn't really do it so much in pre-calc, but in Calc 2, I remember having to know how to rotate a conic back into standard position. So what that means, and we'll visit it later on in this chapter, um, rotating a conic back into standard position basically means that, if a conic looks like it's rotated a little bit, then what you can do is rewrite the coordinates of the conic section so that the axes associated with them lie along the x and y axes if they're out of position to begin with. So sometimes when you do that, it makes problems like integration a little easier if you rotate a conic out of standard position or back into standard position. So that's why I kind of picked that matrix with the trig functions to kind of, pick on a little bit on page 2. Because that's going to be a pretty important matrix for us with regard to this topic. So it says here, in many problems, a rectangular xy coordinate system is given, and a new x prime y prime coordinate system is obtained by rotating the xy coordinate system counterclockwise about the origin through an angle theta. So when you do that, you now have two coordinate systems. You have both the original xy coordinate system, and you also have the x prime y prime coordinate system. So let's think about this for a second. There's a point Q in this diagram, and according to the illustration here, Q has a set of ordered pairs. It has an ordered pair using x comma y, and it also has an ordered pair using x prime y prime. So the ordered pair xy is based on the xy coordinate system. That probably goes without saying. But when you rotate the xy coordinate system by an angle theta, you create two new axes. You create what's going to be an x prime axis and also a y prime axis. So with that, with the assumption that that forms a second coordinate system, then we have two different ways of expressing the ordered pair for Q. We have xy, and we also have x prime, y prime. Now, this actually relates to something we were doing back in chapter 4, where it was a change of basis. So the ordered pair x comma y would be based on these two basis vectors, I and j. Now, if we want to obtain the x prime, y prime coordinate system by rotating the x-axis and y-axis by an angle of theta, then naturally these two vectors are going to be rotated counterclockwise by that same angle. And when you do that, they yield two different basis vectors. So I'll say it this way: when we rotate I, we'll get the basis vector, I'll call it u1 prime. And with that, I doesn't necessarily have to be the basis vector for the xy coordinate system. So just to be a little more general, I'll say that this is u1. And then when you rotate the vector j, which you can be a little more general with, calling that u2, it turns into a different basis vector, namely one for the x prime, y prime coordinate system, and that would be u2 prime. So long story short is we're going to want to be able to go back and forth between an xy coordinate system and an x prime, y prime coordinate system. And the way to do that is actually doing something we've done before. Um, it involves using transition matrices. So you might recall from chapter 4 that we were constructing this matrix P, which would take us from one basis to a different basis. And keep in mind that if you have a basis in a vector space, you can create a coordinate system with it. So basically, to go from one basis to another basis is equivalent to going from one coordinate system to another coordinate system. And we're going to look at the matrix that does that for us. Actually, there's going to be two of them. There's going to be the matrix that takes us from the xy coordinate system to the x prime y prime, and then there's going to be one that takes us back. So let's say that we wanted to go from the xy coordinate system to the x prime y prime coordinate system. Then that would require a transition matrix P, and if we consider the old basis B, the xy coordinate system, then we would want to go from B to B prime. Okay, so this is a matrix that we're going to use to go from the xy coordinate system to the x prime y prime. And the matrix that is used to do this looks very similar to the matrix we were working with on the last page, but it turns out it's inverse. So let me go ahead and populate this matrix. The first column has cosine theta, negative sine theta, and the second column has sine theta, cosine theta. Okay, that's one transition matrix. A second transition matrix is going to be the one that goes in the opposite direction. So a transition matrix which takes us from B prime back to B. And in this context, this matrix will help us go from the x prime y prime coordinate system to the xy coordinate system. And it turns out that the matrix for this is the inverse of the matrix I gave you in, of the first matrix that I gave you, P from B to B prime. And since, these matrices are orthogonal, the inverse is just a transpose. So this is going to look very similar to matrix 1, but it's going to be different in the sense that it's its transpose. So the first row is going to be cosine theta, negative sine theta. And then the second row is going to be sine theta, cosine theta. So notice that there's no variables x and y involved here. So you might think, okay, well, if I have this rotation matrix and I want like an ordered pair xy, how do I get that? Or if I want an ordered pair x prime y prime, how do I use these to get those particular x prime y prime values? Well, those are going to be based on what are called rotation equations for two space. And essentially what happens is if we want the x prime y prime coordinates of a point in the xy coordinate system, we take the transition matrix, which goes from B to B prime, and we multiply this matrix. I'm going to put it in brackets just so you understand it's matrix. We multiply this by the original coordinates of the point x comma y. And in doing so, you get formulas for both x prime and y prime. The formula for x prime goes like this: x cosine theta plus y sine theta. Okay, so you'll need to know the angle theta, and also you'll need to be provided the original x and y coordinates to get x prime. To get y prime, it's a little similar here. We get negative x sine theta plus y cosine theta. So again, to compute the y coordinate or the y prime coordinate, you're going to need to know the angle theta and also the original x and y coordinates. There are formulas which help you go back from x prime, y prime coordinates to just normal x and y coordinates. And that would be found by taking the transition matrix going from B prime to B and multiplying that to the x prime, y prime coordinates. And what you end up getting is a formula for x based on x prime and y prime and theta. It goes x prime cosine theta minus y prime sine theta. And then the y coordinate would be x prime sine theta plus y prime cosine theta.